Today lecture we want to look at matrix and system of linear equation. Matrices arise in many ways in most of our problem as we study a system of equations, and most times in mathematics and in engineering and physical sciences, most of our problem we try to model mathematically, sometimes even in differential equation. We sometimes bring them into a matrix form so that we can simplify it and then apply some mathematical methods. Today I will be taking you an introduction part to matrix. What you can see in equation 1 is just a system of linear equation. If you cast your mind back to your elementary linear equation where you did simultaneous equations, you say when you are solving for two unknowns and with two equations, then you can say that equation is simultaneous. But you can go further, there are many finitely solutions of unknown. Like this, you have x1, x2 to xn. You want to find this solution. So what you just need to know with the application of matrix, you'll be able to solve solution like this. That's why we talked about matrix, using matrix to solve systems of linear equation. There are some words I will just explain. When you have the B, this B here is what we call the homogeneous term. While the AIJ, you can see A1, A12, as we call AIJ are coefficients of the equation. You can see it, the AIJ. And we say that this equation 1 is homogeneous if B1, B2 to Bm is equal to 0. I will say if at least one of the Bi is not vanishing, that means one of this one is not 0, then we can say it's non-homogeneous. This equation here, we have put it in the form of this matrix. So that's why you can say this is A, this is B. This elementary knowledge, we don't need to waste time. Entries of matrix are the element. You have the row matrix, you have the row matrix, column matrix like this. This an example of this matrix is A matrix A. We call it 3 by 2 matrix. How do you name the matrix? The row multiplies the column. The number of rows here is 3. The column is 2. You see 3 by 2 matrix. Here, this is a row, this is a column matrix, or we call it column vector. This is also a row matrix, or we call it row vector. We can put matrix in the form of a curved bracket or a square one, depends on the textbook you use. And when we have this matrix, we put it in a bracket form. But when we have an enclosure in a physical line, what we are talking about is the determinant of that matrix. Now, basic definition of a matrix is when you have the m by n matrix. It's just an array of m and n entries called the element. The m rows and the n columns that you see here. These are the n columns, m rows. So we can say this matrix is m times n matrix. Another word you can also use is you can also represent the matrix as I and J. That's matrix Aij. What I simply means element in I, just an I row, while the J columns. Just a form of what you know. This like this single matrix you say that has single element. It's still a matrix, but we'll just say it's 1 by 1 matrix. This 3 by 4 matrix it has, and we will say this type of matrix we also call it real matrix because the entries, the element is array numbers. This is a 2 by 2 matrix, but we call this one a matrix with a complex number. This is also a matrix with a functions, where you can see you have functions of trigonometry functions. This also I've explained this is 3 element row vector, while this is 2 element column vector. A square matrix simply means a matrix where you have equal number of row m equal to the number of column n. An example of it is this: a 3 by 3 matrix, 2 by 2 matrix, 4 by 4 matrix, and squared matrix. The definition of equality of a matrix: if I have matrix A, Aij, I have matrix B, Ij. And this matrix is in a form of P times Q, M times N. This matrix A and B will only be equal if and only if there are two conditions to look at. If A and B, that's matrix A and B, have the same number of rows, the same number of columns, so that we can say M, that is the column, the row here is equal to the row here. The N, that's the column, is equal to the column there. You can see this matrix is the same, is equal rather, not the same. B, the other condition is that where you have matrix A, Ij and matrix B, Ij, if they are equal, then you can say this is equal to this for each I and J. Now see this example. This matrix A, look at the entry on the element. Matrix B, you have this entry. Matrix C, you have this. Now, A is equal to B, but you see it satisfies the first condition because they are the same. You have the same number of rows, the same number of columns. Now, but there's other condition it has to satisfy for A to be equal to D. You have alphabet there, B here in A must be equal to, your B must be equal to -3, while your A must be equal to 9. It's only then, if and only if, this A is equal to B. You can see clearly that A cannot be equal to C and B cannot be equal to C. Definition of multiplication of matrix. A matrix, definition of matrix addition, not multiplication. Matrix A and B is only defined if the matrix have the same number of rows and the same number of columns. What we say is that a matrix is defined, or addition of a matrix. We can carry out an operation of addition on a matrix if we have the same number of rows and the same number of columns. That's what you can see here. That's the explanation there. Now, a matrix that we can add is said to be conformable for addition. There are some matrices we cannot add. Such matrices are not defined because the number of rows are not equal to the number of columns. Now, there's the commutative law is satisfied in addition. What I'm saying is that if I have matrix A and B, A plus B is equal to B plus A. We can say that the matrix addition satisfies the law of commutative. Definition of transpose of a matrix. If I have matrix A, and matrix A see that's matrix Aij. Now, when I interchange the matrix A, I interchange the row by the column. Then I produce a new matrix. This matrix M times N. So by the time I interchange the row, can you see here? This is the row I becomes the column. The column J becomes the what? The I. So such type of matrix is what we call a transpose matrix. These are examples of a transpose matrix. Now for the rest of this course in this material, when I put T by matrix, perhaps what I'm just telling you to find the transpose. This matrix A, the transpose of A is this, where the rows becomes the column. This is matrix A, the transpose is this. You are going to see some problem as we solve in this material, where I just put the matrix and I put T off script, upper script. So I'm just telling you it's a transpose of a matrix. Definition of scaling a matrix by a number. Let's just call this. You multiply a matrix Aij, that's matrix M times M matrix, by a scalar. A scalar can be a real, can be a complex number. For example, I have lambda to be the scalar. I can scale the matrix. Just multiply that matrix by lambda. It becomes lambda Aij. This is an example here. You have lambda to be 2. And this is matrix A. Then lambda A simply means 2A. That means 2 multiply this matrix, I have this. Assuming I have lambda to be minus 1, this is saying that minus lambda, lambda A, is the same thing as minus 1 times matrix A. That's minus A. Minus multiply this matrix, I have this. Now, there's something you need to apply to. I've just done that of addition. Now, we can as well look at the difference and subtraction of matrix. With the definition of addition and scaling of matrix, it also shows that matrix A and B are conformable for addition. Then the subtraction. If a matrix A, matrix B are defined by addition and scaling the matrix, then the subtraction of B is also can be also be defined. This is just if I have matrix A minus B, the same thing as A plus minus, that's the scalar, minus B. So it's just like saying A minus B. Look at the example of this matrix A, matrix B. A minus B, you have that. There's what we call none or zero matrix. When the entries, every element in the matrix is 0, you call such matrix zero or no matrix. And when the minus A matrix, we call it negative of A. This is just a simple algebraic law that A minus, take A matrix A from A is the same thing as say A plus minus, that's the scalar lambda minus 1 times A, it gives you 0. That's a null matrix. Definition of product of row and column. If I have a matrix A, these are in a arrow element row vector, and then I have matrix B. This is a arrow element row column vector. But you see, the way we put it here, you may think that this is a row and B, that's arrow element column vector. But because of this T here, we test you a transpose. That's why you can say arrow element column vector. So what this is saying is that when you multiply A by B, this is what you will have. That is A multiplied B. Now I need to say something. You need to know that the product is only defined, that will say the product of two matrices A and B is only defined when the number of elements in the row vector, that's the row vector A, I can say matrix A, is equal to the number of elements in the column vector B. Look at this an example here. I have these two matrices. These are row vector matrix. This a row matrix, and this also a column vector matrix. And you see here, I want to multiply this by this. They say that if this product is defined A and B, then the number of rows, the number of elements rather, in the row vector matrix must be equal to the number of elements in the column vector matrix. Now that goes us to see the same definition when you have the multiplication of matrix. The first one is just a column and the column vector, arrow element column vector, multiply arrow element row vector. Now assuming you have matrix A, see the same matrix condition is satisfied, that the product of matrix A is only defined if the number of column in A is equal to the number of rows in B. With an example, this is just a further explanation of what is in the first one, but let me just use perhaps an example later. Now, when matrix A and B is defined, we say when do you say matrix A and B is defined? Yeah, a matrix A and B is only defined if the number of the column in A is equal to the number of rows in B. So we can say, look at this one, this AN times M times N matrix, P times Q matrix. We can see here that N is equal to P. So once the product A and B is defined, then the matrix is said to be conformable. All we say is that conformable for matrix multiplication. It is important to know that the law of commutative is not satisfied for matrix multiplication. The law of commutative, where you say matrix AB is not equal to BA. You'll see that from this example. But in addition, A plus B, matrix A plus B, is equal to B plus A. But in matrix multiplication, you said is non-commutative. In fact, this guides us when we are using the concept of matrices as we look at some applications in genes. And we want to ask, when we want to model in solving real life problems, sometimes medical aspects, we want to ask, is this element, this vector I'm introducing, is it communicable? And then those are things like we are faced with the challenge of the pandemic. Sometimes we want to write some model in mathematics and seeing how we want to provide some scientific approach. The things we have is that when we have equations, the variables in those equations we are introducing, we ask ourselves, does it communicate? Is it commutative? So those are things that guides us when we are using matrix. So when the matrix provided, okay, that's conformable. I've said much about conformable. Look at this example, you can see that yourself. So just excuse me. Okay, you can see example 3.6 yourself. And then when you multiply matches AB, you have this. When you multiply matches BA, you have it. You can see that A matches AB is not equal to A. Now, I can go further to say that we can write a simultaneous equation of matrix of, if you go back to my equation 1 when I started, and I think I told you about simultaneous equation. That equation 1 you see at the beginning, we can express it in this form: AS equal to B. AS equal to B, where S is just the row, and this no longer is a column because of the T, and where your A is your quotient matrix, your B, that's where I talked about homogeneous. Now let's look at some basic law. I will not bother to prove it for you, but just know that associative and distributive properties of matrices, these are true. I think I've explained this. This is associative, and this also associative. This is distributive. This is distributive. So these are some basic law. You can prove some of them yourself. Transposition of products. We know that these are theories in matrix, and I will not bother myself with the proving, but just to know, for you to understand that if I have matrices A and B and these matrices are conformable, go back to your multiplication. For a matrix to be conformable, what is that telling us? That that matrix must be defined by your multiplication, matrix multiplication. So it can form a product where you have AB transpose is the same thing as B transpose multiply A transpose. The proof is here. I don't think you will need the proof, but you can just look at that for your own personal. Now, from the proof of that theory, we can raise a matrix to the power. If I have A n times, what I'm saying is A to the power of n. It's the same thing as saying from your knowledge of indices, A to the power of n dot A to the power of n. The same thing as say A to the power of n plus 1. So we can arrange matrix n. You see this one when we are looking at, but this condition is only when the matrix is a square matrix, matrix A. Now, okay, these are just further laws of addition. These are just further on the law of transposition. Now, this is just talking about difference between ordinary algebraic equation and matrix equation. This, if I have match A, your normal algebraic equation, you have A, B is equal to 0. This saying in which A and B are element, not both of them. We know from our elementary mathematics, we are going to see that when you are looking at linear dependence and linear independence. If I have A, B equal to 0, what comes to my mind that the element A and B, both of them which are 0, it can either be A is 0 or B is 0. And sometimes I can have A to be 4 and B to be 0, then I'll get this. So what it's telling you, it implies that it's not necessary that both the elements are 0. It's either A is 0 or B is 0. And that also follows true when we look at matrix. When the matrix A, B is defined such that matrix AB is equal to 0, it does not necessarily follow that either A is 0 or B is 0. You will see that before we round up this course. And not only that, there's what we call another aspect I will explain is that if I have my equation AB and equals to AC, where I have numbers A, B, and C, if B with B not A not equal to zero, that's what we call cancellation law in algebra. That means that I can conveniently eliminate, I can cancel this A. If I multiply this by A minus A to the power of minus 1, I will eliminate it. Multiply this from the left side or right side, I will eliminate it. So I can have, that's what we call the law of cancellation. Or from your basic knowledge, if I can divide both sides by A, I will have B to be equal to C. But this does not really apply to the cancellation of matrix factor, as you can see in elementary algebra. Let me just explain that with this example. See this matrix, consider matrix A and B. Matrix A and B, you see the elements are not zero. I can say, but when you multiply A, matrix A, AB is zero. But neither A nor B is a null matrix. That explains this. Now, come to the example 2. I have matrix A, B, and C. Now, if I multiply A by A, AB, and I multiply A, B, A, C, I'm going to have this. So then, A, B, A, C is equal to this. But B is not equal to C. That's something you need to take a little bit your knowledge of elementary this thing into. You can see that A multiply A by this, matrix AB, AC. It gives me this. And they are equal. AB is equal to B. But that explains the second concept in that algebraic equation, that B is not necessarily equal to C. Now there's what we call leading diagonal. When you have the element in a matrix A1, A11, A12, A22 to what we say, let's say ANN, that circle, for example, this line here, is what we call the leading diagonal of a matrix. And the sum of this leading diagonal of a square matrix is called the trace of a matrix. And now when you have a matrix where all the elements away from the leading diagonal are zero, but not every element in the leading diagonal is zero, you call such matrix a diagonal matrix. And when you have a matrix where all other elements in the matrix, outside the leading diagonals are zero, and you have the leading diagonal as 1, we call such matrix unit matrix or an identity matrix. We always denote it by this 1, this I, the unit matrix or identity matrix. These are theory in matrix that if you have a matrix M times N, the identity of M multiply A is equals to A multiplied by N identity. That's where I have now. Okay, if I have matrix A N times M times N matrix, what I'm saying is I have a matrix, a square matrix, and I multiply that square matrix either from the left or from the right multiplication by the identity I'm going to have the sender matrix. This guides you when you are applying the matrix to solve system of linear equations. By the time you are going to see, if time permits, other course, but just know that when you multiply a matrix either from the left, you see where the identity now comes, but you know that Or you have matrix A, B. I mean, when you multiply matrix A by B, it's not equal to multiply B by A. But in identity, you can see whether you multiply from the right or from the left, or you multiply matrix A from the either from right or left, you will have A when you multiply by the unit matrix or the identity matrix. Now, this is just an example of a diagonal matrix. I told you a diagonal matrix is where the other element on the diagonal are all zero. And the leading diagonal, not all of the elements are zero. This is an example of a diagonal matrix. Now, the trace of a diagonal matrix, the trace of a matrix is the sum of the leading diagonal. 3 by 3, this is an example of 3 by 3 unit or identity matrix. And it's also a diagonal matrix where other elements, apart from the leading diagonal, are 1. There are special types of matrix where you have a matrix where all the elements below the leading diagonal are 0. Where you have all the elements below the leading diagonal are 0, we call such matrix upper triangular matrix. Now, when you have all the elements of a matrix above the leading diagonal are 0, we call that one a lower triangular matrix. Now, when you look at a matrix, a symmetric matrix is a matrix where A is equal to the transpose of A. I have matrix A. The transpose of that matrix is equal to A. We say that matrix is symmetry. When we say skewed symmetry, if I look for, it's telling me that the transpose of A is equal to the minus of A. That means is that if matrix A is skewed symmetrical or say skewed symmetric matrix, it means that the transpose of A is equal to minus A. We try that this is a skewed symmetric matrix, this is symmetric matrix. Now, orthogonal matrix Q. Now, orthogonal matrix means is defined as a matrix. I multiply that matrix by its transpose is equal to the transpose of that matrix multiplied by itself, and it gives you the identity. Such matrix is what we call orthogonal matrix. This is an example of an orthogonal matrix. You can confirm that yourself. Now, this from the above, I've talked about real value matrix. I mean, real value matrix. I'm going to talk about on a real plane. Now, if we now have elements on Aij as complex number, now look at this. We call a matrix. This A bar simply means that the elements here are my complex conjugate. Can you go to your, we have done something on complex number, you know, complex conjugate. Now, if I say matrix A is Hermitian matrix, what I'm saying is that the transpose of the conjugate of that matrix is equal to A. I can say matrix A is Hermitian matrix. A skewed Hermitian matrix simply means the transpose of the conjugate of that matrix. You try this on your own. This is an Hermitian matrix. This is a skewed Hermitian matrix. That means the transpose of this matrix A gives you minus A. Try that, you will see that these are examples of a Hermitian matrix. Before I round up the course, I want to talk something about block matrix, as we can partition matrix into sub-matrix by either considering horizontal line or vertical line. Sometimes you will look further that there are some matrices you will have that the entries into that matrix may be very large and you want to multiply. Perhaps sometimes you want to even find the determinant of that matrix. How do you go ahead with such matrix? That's where the context of blocking we partition such matrix. Look at this matrix, for example. This is matrix A, 3 by 3 matrix. I want to partition this matrix. I want to put the matrix into block. You see, I can by different blocks where each element itself is a matrix. That's the concept of block matrix. I partition A. If I partition matrix A, where each element in that matrix is a matrix itself. That's what we talk about block matrix. And such group, we call them sub-matrix of A. And let me just explain with this example. If I have this matrix and I want to partition this matrix, and partition, yeah, let's say I pick these two lines, this fourth row, I partition it with a straight line, just dot, dot. And I partition here, vertically and horizontally. You will see what will happen here. For me, I'm having matrix A11, and I have matrix these two, matrix 1, 2. Here I have matrix 2, 1, that's A21, and this 0, 0 is A22. Now, and I have from this matrix A, I can write it in a block matrix of this form. What I mean is that this is this. Look at this, you can see it. A21, that's this, is what? Matrix. The element there is 1, 2, 2, 1. A22, this element is a row, a column vector matrix. Now, the addition and scaling a block matrix follow the same rule for ordinary matrix for what we have done so far. Now, if I now look at, you can see from this one, I've partitioned this matrix into these sub-matrices. Now, if I want to see how the multiplication of a block matrix is performed, now let's look at this example, this 3 by 4 matrix. Now, we want to see how to perform a kind of multiplication of A. This A, this is B rather. So now, what do? We want to say that A and B, when I say matrix A and B, I want to look at this matrix. I want to multiply this matrix A by matrix B. And you don't forget that the matrix is conformable. Why? Because the element in the row of A is equal to the element in the column of B. So I can say for matrix multiplication of AB is conformable. So then, how do I go about it using partition? So what I can do is to partition B. I want to find A matrix, the product of A and B. Then I want to partition B. See, I partition it this way, vertical and horizontal. So I'm going to have 4 sub-matrices. This is B11. This is B12. You see that? Okay, it's here, you see it. This is B12, that's this matrix. This is B21, that is 2. This is B22, that's this column matrix. Now, multiply this, your block matrix you have gotten, your partition A, this matrix B, the partition 1 by this. When you multiply it, you are going to have this. We have condensed this matrix. That's the simple mathematical concept. We have a matrix we want to multiply, but we have condensed it in a simple form. And I've told you that why do we need to partition matrices is because sometimes you may have a very large matrix and you want to find the determinant of that matrix, or perhaps you want to even multiply. But when you partition it, you condense that matrix. So when you multiply, this is what you will get. Now, for you to do that, you practice that on your own. I want to just explain this one for you. This A11, B11 plus B12 and B21. Now, when you check here, your BA11 and B11 plus B12 times plus B12 times B21 gives you the matrix 4. That's like a unit matrix. How do we get that? Now come here. What is my A11? This is this matrix. What is my B11? Now, because I'm using slide, this multiply this. Think of this. This the row multiply this, it will give you 0. You can do that on your. This multiply this gives you 0. Now you now have this to be 0. Now A12 multiply B21. A12. Where is A12? That's this. Multiply B21. Where is B21? That's this. That matrix multiply that gives you 4. 0 plus 4. That's how you have this unit matrix 4. You can try that for the others yourself. After you have gotten this, you will now put it back into this matrix you have partitioned. You get this, you put it, you get this. Now, this is your answer. You will get when you do direct multiplication. Try it yourself when you do direct multiplication. So what we are just saying is that the calculation of matrix product using partition matrix is applicable when we partition A and B to perform in such a way by the product of their submatrix. Matrix partitions has various use arising in machine computations, and sometimes in when you have tried to look at a problem and you have a large fixed matrix A and you want to multiply it by a sequence of a very large matrix like PQ dash. So what comes to your mind is block matrix. If I is significant in describing complex oscillation problem that is governed by a large system of simultaneous ordinary differential equations. In fact, problems like this arise from the fact that matrices of the coefficient of equation contain many non-submatrices. So I have hope that with this lecture material, I've introduced you to matrices, and I will send you the material on the. I'll send you this video and as well as the lecture material for you to go through. Thank you for your understanding.